Welcome to Chapter 21, Podcast 3. This is all about determining standard voltages. So a standard voltage is given the symbol of E naught, right? Remember, naught means standard. And E in this case is our voltage. All right, so voltage is not given the symbol V. Again, it was used up somewhere else in our chemistry, and so we went with E in order to say voltage. And voltage is basically just a measure of an electrical potential between two things. It's like how well will electrons flow between these two species, right? And so that's what we're going to calculate there. The bigger our voltage, the easier it is for our electrons to flow between two things. That's all we're kind of calculating. Voltage is like a weird kind of topic for us to kind of wrap our minds around sometimes. So if you want to like Google something like what is voltage and read up on it a little bit, please do. That would help out a lot sometimes if you don't understand what voltage is. But I'm going to teach you how to calculate these standard voltages. So when we're talking about standard voltages, right, and again we give that the symbol of E with an R naught symbol, right? The voltage, right, by definition is what drives our electrochemical reactions to take place. Right? We need like a difference in voltage from one species to another for our oxidation reduction reactions to happen. Right? Something is not going to lose electrons and give it to another species unless they both, like, unless the species that wants to lose electrons wants to lose it to a certain extent, and the one that gains it wants to gain them. Like, you need to have, like, some cohesiveness there. Right? So both of those things need to be occurring, and that is what we're calculating when we calculate our voltages, making sure that something is happy losing some electrons while something else is happy gaining those electrons during that chemical reaction. When we talk about voltages, we say that this is an intensive property. Okay, now, right? This says that it is independent of the number of electrons flowing through the cell. What we're going to find then is that what it really depends on is the reaction itself and not the number of coefficients and stuff like that. So when we look up a voltage, right, we're going to be able to look up voltages for things. So we might see the voltage of, say, something like copper 2 plus 2 electrons forming solid copper. And we can look up a standard voltage for that. Is equal to some number. I don't know what it is. I should have looked it up before I did my example, but we're in too deep now, so it's some number. What this really means is that when it says it's independent of the number of electrons flowing through the cell, what this really means is that if you had 2 copper 2s plus 4 electrons, producing 2 solid coppers, our standard voltage is equal to some number. And these two are going to be the same value. Right? It's independent of the number of electrons flowing, so it doesn't matter whether we have the 2 from our copper 2 being reduced down to copper, or 2 copper 2s being reduced down to 2 coppers and having 4 electrons flowing. The voltage is going to remain the same either way. All right, and then lastly down there it says that our standard voltages are measured with, all right, well, they're standard values, so remember that that means that anything that's aqueous is going to have to be 1 molar, and anything in our reaction that is a gas in the gas phase is going to have to be 1 atmosphere. That's how we're going to calculate our standards. Now, guess what? I bet you figured out that later on in the chapter, after we've learned how to calculate standard voltages, we're going to see what happens when we're not at standard conditions. But until then, we're going to stick with looking at how to calculate standard voltages first. Let's take a look at the standard voltage, or E naught, for just some sort of a generic standard cell. All right, and we'll see why I'm going to use this as an example in a little bit. Right? Now, when we calculate our standard voltages, it can be a little bit difficult to understand why we do things the way we do them, but calculating themselves should not be super complicated. So we're going to go through why we do things the way that we do them first. Then we're going to look at how we calculate them and what that means to everything else, probably in podcast 4. So here I've got zinc reacting with some strong acid. All right, well, that strong acid is aqueous, so it's got to be 1 molar for standard solution, right? And then that's going to become zinc 2. Again, it's got to be 1 molar because it's aqueous. And we have produced some hydrogen gas at 1 atmosphere, right? All those things are at standard conditions. Our temperature has to be constant. And in this case, we're going to keep it constant at 25 degrees Celsius because that's room temperature and that's where we like to work, right? We don't like to work when it's like 0 degrees Celsius. That's not very much fun. We wouldn't like to work when it was like 100 degrees Celsius either. We would burn alive. So under these conditions that are set up, what we find, right, we can separate these 2 half reactions, we can put an external wire through it, and we can hook it up to a voltmeter. And that voltmeter is going to have the little needle go over, and it's going to read that the voltage for this reaction is 0.762 volts. And you're like, great, that's a way that we can calculate the voltage of something. And sure, we can calculate the voltage of something by running the experiment and looking at what comes up on our voltmeters. That's one way that we can do this. But what if we're sitting there, we have like a chemical reaction where we don't really want to spend the time to do this in the lab. We just want to be able to calculate the voltage. Well, another way to do this is we can calculate the voltages of certain things, and then we can combine them into our overall reactions and solve for them. That's what we're going to look at doing in our next slide, or 2. When we want to calculate the standard voltage of something, we're going to calculate the standard voltage by taking that the standard voltage, which is our E naught, is equal to the voltage of the half reaction for the reduction, right? That's our half reaction for the reduction half, plus the voltage for the half reaction of our oxidation, right? Every single one of these reactions, right? They're all redox reactions, and we can separate them into a reduction and an oxidation half reaction. They can all be done that way. So let's go back to the reaction that we had on the previous slide, which is zinc plus our 2 strong acids producing zinc 2 and 2 hydrogens. So this would be able to be separated into, right, our zinc becoming our zinc 2 plus 2 electrons, right? This is our oxidation half step, right? Again, I know this because the charge is going up. I know this because the electrons are products, right? Those things tell me it's the oxidation. And then we also have our 2 H pluses, plus 2 electrons are becoming hydrogen gas, right? And remember that this is our reduction half step. I know that again, right, because we're reducing the charge on the H from +1 down to 0, and that the electrons are on the reactant side. Now, if I want to know the voltage, right, we hooked it up to a voltmeter on the previous slide, and we found that our voltage was 0.762 volts. And I know that that is equal to the voltage of the reduction plus the voltage of the oxygen. All right, now the problem with this, and where I said that like the way that we get there can be a little bit confusing, but calculating is not, is this top bullet point says the value of E naught, right, cannot be measured for a half cell. So what that's telling us is that we cannot calculate either of these 2 things that we need to solve for this problem. It's not I can't calculate it. The reason that we can't calculate them is because I cannot have a reduction reaction happen without an oxidation reaction happening. So if I wanted to know what the voltage of H plus to H2 is, right, what that reduction voltage is, I can't hook up H pluses to a voltmeter and see how the voltmeter reacts whenever we produce hydrogen gas, because it's not going to happen unless an oxidation is taking place at the same time. It doesn't just happen by itself. I can only get that to happen if an oxidation is taking place, like our zinc producing our zinc 2 cations. So what we did is we decided that, okay, what if I just said that the reduction of H plus 2H pluses to our H2 gas, what if I just said that the reduction of that was 0? All right, well, then I could plug that into our equation. Right? And I could say that 0.762 volts is equal to 0 plus E naught oxidation for our zinc to zinc 2. And so the E naught oxidation for zinc is going to be 0.762. All right, now, is that exactly what the value is? Don't know what the value is, but now, right, we have that value. And I could say, okay, what if I had our zinc, right, plus our copper 2 is now producing our zinc 2 plus our copper. All right, well, I now could say, all right, what if I wanted to know the reduction for copper 2 to copper? All right, well, I could hook up this entire reaction to a voltmeter, and if I hook that up to a voltmeter, I would get some E naught from experiment, right? I'm going to get an E naught from an experiment that's equal to our reduction for our copper 2 to copper plus the oxidation. Well, I just said that the oxidation is 0.762 volts. So then I could solve for what the reduction is for copper 2 to copper. And then I could use that to solve for something else and something else and something else. And then all of a sudden we have this giant table of these things that we're going to call reduction potentials. Once we have all those reduction potentials, now we can just add those things together and we can see what the overall voltage is going to be. Now that we've defined that our hydrogen half cell is going to be 0 volts, right? We could use a strong acid to calculate the other half cells and measure it in relative to that value, which we could find in a whole bunch of different things. And then we can mix them all together. And once we start doing that, we can put together something that's called a table of standard potentials. All right, now when we have these standard potentials, they're always going to be written as reductions. So everything in our table of potentials is always going to be a reduction. So we're always going to see our electrons as reactants. We might have to find when they're oxidations. So what we need to do is, if we want to find the oxidation of something from one of these standard potential tables, is we're going to take the equation that's given to us. Say that it was zinc 2 plus 2 electrons forming solid zinc, right? That's the reduction of zinc 2 to zinc. And we have the reduction potential for that as being negative 0.762 volts. Now, if I actually wanted it to be the oxidation, what we're going to do is we're going to flip that reaction around. So notice that I'm reversing the reaction. So zinc is now my reactant, producing our zinc 2 plus our 2 electrons. That's what we've been seeing all chapter long. That is the oxidation of zinc to zinc 2. Well, notice that the value for the voltage, the standard voltage on that, is the same, 0.762, but it's just the opposite sign. So when we need, and we will, when we need the standard voltages for the oxidation of something, right? The voltage is the same as what we see as the reduction in a standard potential table, but it has the opposite sign, right? So it's equal in magnitude, it's the same size, but it has the opposite sign. So if it was negative, it's now positive. If it was positive, it's now negative. Our next slide is going to show a table of reduction potentials. So it's going to show a whole bunch of half reactions, and all of those half reactions are going to show reactions, and then they're going to show the standard voltage for the reductions, right? When we have a table of reduction potentials, we always show oxidizing agents on the left side. Remember from Chem 1, hopefully, and know that like the terminology for redox stuff can get confusing. But an oxidizing agent likes to oxidize something else, and it is usually reduced, right? In fact, if it oxidizes something, it has to be reduced. Reducing agents reduce things. It is a thing that is oxidized. Reducing agents are always located on the right side of our reduction potential tables. All right, so it says that the more positive our reduction voltage is, the stronger the oxidizing agent. The more negative it is, the stronger the reducing agent. So you've got to remember, more positive, right? Not only more positive, it's stronger oxidizing agent, and is on the left reactant side. More negative is a strong reducing agent, and on the right, which means that it is a product. All right, so if you're given a table like we're going to see, right, make sure that we remember oxidizing agents are on the left, reducing agents are on the right, and then look at, right, how strong positive or negative those things are. The table we're going to see on our next slide has those things labeled. Probably the one that you get on an exam will not be labeled, so prepare for that. Be able to know these rules in order to answer a question that has to deal with that sort of a thing. Here we have a table of reduction potentials, right? Again, they're always reductions whenever we have these things, right? Now, notice that our oxidizing agents are on the left-hand side. So something like fluorine is a very strong oxidizing agent, right? It really likes to oxidize other things, meaning it really likes to be reduced itself. Whereas if I'm looking at reducing agents, right, really strong reducing agents have very negative voltages, and the reducing agent has to be on the product side or the right-hand side. So something like lithium is a really strong reducing agent, meaning it really likes to reduce other things, and thus it really, right, wants to be oxidized itself. I get it. Some of the terminology on these things can get a little bit confusing, right? But right, once we kind of get that down, if you can get it kind of crammed in there, it'll help out a lot on being like, okay, this is reducing it, this is strong, this will do this, and this will do that. So get those little rules down. Right. We're going to start off our next PowerPoint looking at this table of potentials again, because we're going to need to use this table of potentials in order for us to actually calculate standard voltages and to determine whether some things redox values, whether it's going to be a strong redox reaction or a weaker redox reaction. We can calculate that by looking at this table of potentials. So in podcast 4, those are some of the topics that we're going to be looking at. I'll see you then.